Good morning or good afternoon, everybody, depending on where you are. I'm Christian Pinto from IBM Research Europe in Dublin, and today I will, let's say, introduce you to ThymesisFlow. That is our open source hardware-software framework for software-defined disaggregation that is based on OpenCAPI. So if you're familiar with the OpenPOWER Summit, you might also be familiar with the ThymesisFlow as well, because last year there was an extensive presentation of the hardware design. So today I will just quickly go through a few details of the design that you need to know for the rest of the presentation. But I want mostly, I mostly want to let's say concentrate on the software stack that we have built, and then the evaluation that we have done using this software stack. So let's start from the beginning. Okay, so what is this software-defined memory disaggregation? You've been hearing a lot about today about disaggregation and composing cloud, also the P10 talk that was great, right? So essentially, when we say software-defined memory disaggregation, is that in a classical system, you have in the data center, for instance, you have a series of boxes. Each box has CPU, memory, network interfaces, and the application and operating system run on each of these boxes, thinking that the peripherals that they use are physically in those boxes, and they are actually in these boxes, right? In a software disaggregated setup that you see on the right, the application and operating system are running on a kind of abstraction, right? We call it software-defined compute node, and it is essentially an abstraction that we create in software that fools the operating system and the application of thinking that, as usual, all the peripherals are on the same node. So in this case, the OS thinks that there will be one CPU and two memories on the same node, while actually part of these peripherals are located physically on another machine. So they are disaggregated. And this is made possible because all the machines that participate to this disaggregation system are connected via the custom disaggregation fabric. So if you think, if your application needs more memory than what you have on a node, in a classic setup, what you would do is essentially you would scale out on two nodes. So you run two instances of the application. These instances interact and synchronize via network, and then you use the memory of both nodes, and you're happy because now you have enough node, which is more than the memory available in one node. But what can happen is that, as you can see on the left, there is CPU free, but this CPU is jailed. These CPU resources are jailed because the memory is all completely used in that node. So you cannot run any meaningful workload on that CPU. So that CPU resources are simply wasted. While on the right, what you can do is that you can select how to compose the software-defined compute node in a way that, for instance, reduces fragmentation, right? So, for instance, in this case, the result would be that you still have the two nodes and you're still using the resources on the two nodes, but the resources that are left are not jailed because you have a full CPU and a meaningful amount of memory for you running further workloads. In general, let's say, why would you do it, right? Today we have seen many presentations mentioning this topic, but one main reason is that the way data centers are built today lead to low resource utilization and jailed resources in general. This is because the way how memory and CPU resources are consumed have orders of magnitude gap in between. So it's nearly impossible for you to have the perfect mix of machines in your data center so that you can serve any possible workload. So you will end up like over provisioning, and then you will have wasted resources. And this will lead to a high TCO and low energy efficiency of your system. While with disaggregation, what you can do essentially is that you can mix and match resources across nodes, and you can create the perfect software-defined node that is tailored around your application. So what we have done in IBM research is that we have built ThymesisFlow, that is a prototype framework, completely open source, that enables memory disaggregation using OpenCAPI coherent attachment And this disaggregation is completely software defined, and the result is totally transparent from the software point of view. So neither the OS nor the applications running on the system will notice that the memory is part of the memory is actually remote from another machine. So as I just said, it's open source, so you can download the full Verilog sources and also the full software stack. It's there, so download it, give it a go, send us your feedback. Okay, so as I said, I will just quickly go through the design, just a couple of slides to get you started. So this is a very high-level view of our prototype. So essentially, what we are doing is, in a nutshell, is that we are bridging the OpenCAPI N1 mode on one machine with the OpenCAPI C1 mode on the other machine. Now, the OpenCAPI N1 mode, also called LPC, lowest point of coherence, makes it that an OpenCAPI accelerator, an OpenCAPI device is materialized as just a window in the physical address space of the machine. And we use this mode on what we call the compute node, so the node that is borrowing memory from a remote machine. So for this memory, the OpenCAPI device will just be a window in the address space, like if it was any other DIMM. On the other side, instead, which is the compute node, the memory node, so the node that is actually lending its memory to someone else, will use the C1 or accelerator mode of OpenCAPI that allows an OpenCAPI device to master transactions on the bus in a cache coherent way. What we do, essentially, what happens in all this infrastructure is that whenever on the compute side, a memory operation is issued by the processor, this is translated into an OpenCAPI transaction. This transaction flows through our design, and it is replayed at the destination node as an OpenCAPI transaction, almost unchanged. I'm saying almost unchanged because we do just two transformations. One is we change the opcodes because the C1 and M1 modes of OpenCAPI use different opcodes for the similar operation. And we patch the address, and I'll show you in the next slide why we do that. So once you exit the CPU, the counterparts of our design are connected using a circuit network, and we use 100 gigabit SerDes. So every single ThymesisFlow link between two machines avails of 100 gigabits per second bandwidth. And then we have an out-of-band control plane that configures all the actors in this picture. So configures our custom logic at both the compute and the memory side, and also if you have a circuit network, it would even configure the switch. So our design is right now implemented on Alpha Data 9v3 FPGA. I will talk about this a bit later in the presentation. I have mentioned that we patch the address. So why we do that? Because as I was saying, on the compute node, the accelerator is using this M1 mode, meaning that the OpenCAPI device uses the one mode, meaning that we see the OpenCAPI device as a window in the physical address space of the compute node, also called the real address space. So every time the compute node issues an OpenCAPI transaction towards disaggregated memory, this will be using a physical address. However, on the memory side, we are not actually lending physical memory to someone, but rather there is a user space process that is allocating some memory. So in virtual memory, doing a malloc, allocating some memory and makes it available for a remote machine to access via our OpenCAPI accelerator. So essentially, at configuration time, using the out-of-band control plane, we configure a table in our design where we have one offset for each ThymesisFlow memory section, and a ThymesisFlow memory section is 1 terabyte big, meaning that every physical address, every transaction that has a physical address belonging to the same 1 terabyte section will receive the same conversion. The conversion is simply we take the effective address coming from the power from the compute node, and we add the offset, sorry, the real address, we add the offset, and this translates into the effective address at the destination side. So once the translation is done, the new address of the targeted by the OpenCAPI transaction is actually a valid virtual address at the destination node. So this is how far I will go with the design of the hardware, because I want to talk about the software. But these were some concepts that are needed for everybody to understand what we'll be doing next. So we have built a full software stack on top of libcxl. That is the official OpenCAPI library to implement user space drivers. So the first layer we have implemented is called libThymesisFlow. And this libThymesisFlow exports a set of helpers that allow attachment and detachment of disaggregated memory from both a computer and memory node, and also give access to some hardware counters that we have in our design. These counters can be used for monitoring latency or throughput of the data going through the design and in the network between the agents, between the ThymesisFlow cards. And on top of that, the last layer of our stack is this ThymesisFlow agent. So the ThymesisFlow agent is a process that we envision that is running every machine that uses ThymesisFlow. And it is essentially the point of interaction between either the orchestrator and ThymesisFlow, or the user, if the user wants to manually configure the system, and ThymesisFlow. So ThymesisFlow hardware here in the picture is called the ThymesisFlow AFU acceleration function unit. So let's see what is the complete flow for memory to be attached from the software perspective. So it all begins from the memory node. So the orchestrator of the user or the user asks the ThymesisFlow agent attach 100 gigabytes of memory. This results in the agent allocating these 100 gigabytes of memory and making them accessible via the ThymesisFlow design, so our custom design. How is this? And sorry, once this is done, the agent returns the effective address that we will use later on. So what happens if we have a look at the memory map? So on the right, you see the effective address space of the ThymesisFlow agent, so the virtual memory map. Whenever we ask the agent, please lend 100 gigabytes to another machine, the result of this operation is the agent allocating this much memory, so the memory that is requested. This allocation is just as simple as a malloc. And this memory is, for the time being, pinned to avoid page faults, even though some page faults are still there because of huge pages, transparent huge pages. And then once the memory is allocated, the ThymesisFlow agent, using libThymesisFlow and libcxl, will share its own process address identifier, process address space identifier with the ThymesisFlow accelerator. Once the accelerator in C1 mode knows the PASID of the process, it will be able of mastering memory transactions towards the just allocated buffer without the intervention of the CPU in a cache coherent way. Then the virtual address, the base virtual address of this buffer is sent back to the user or the orchestrator. So now the memory node is configured, and we go configuring the compute node. So again, the orchestrator or the user interact with the ThymesisFlow agent, asking attach 100 gigabytes of memory to this machine, and this is the effective address at the remote endpoint. So now the ThymesisFlow agent, the first thing that is done, it will configure the hardware, and essentially it will establish the link with the remote counterpart. So after this is done, the memory is physically connected to the machine, but not yet visible to any application or operating system. So the next step is then to actually hot plug this memory to the running operating system, that is Linux. And then what the result is that after the hot plug, Linux will see some more extra memory, like if you go to the machine and hot plug some new things. Again, if you have a look at the real address, so the physical address memory map of the physical memory map of the compute nodes, of the compute node, normally you would see on the machines that we use, the AC922 POWER9 servers, you would see two NUMA nodes. Each NUMA node has, of course, a local CPU and some local memory. So whenever we attach some disaggregated memory that is being borrowed by another node, the result is that this memory is hot plugged into a new NUMA node that is a CPU-less NUMA node and memory-less. Essentially, when we boot the machine, we have slightly modified the firmware so that it creates this memory-less and CPU-less NUMA node that we, let's say, for later usage. So essentially, the agent will configure ThymesisFlow with the effective address received. So it will compute the offset and will write it in the table for patching the addresses. And then we'll hot plug those physical addresses that are assigned to the OpenCAPI device as memory to Linux. This hot plugging uses the let's say, default hot plug functionality that is available in Linux. We haven't modified that. It's a plain hot plug. And the only thing that we do is that we hot plug it as zone movable, which means that the kernel cannot allocate permanent data structures in it, because this would prevent us hot unplugging. So we could not, essentially, if the kernel allocates something there, we cannot detach the disaggregated memory anymore, while we want to keep this dynamic behavior at all stages. And one thing that might be interesting to know is that the base address of this hardware, of this physical memory map, physical area that we hot plug, is actually decided at boot time by the skill boot firmware. It's essentially the window of addresses that is associated to the LPC device, to the lowest point of coherence. So to the OpenCAPI device, they associate 4 terabytes of physical memory map. Meaning that since we use 1 terabyte sections, each OpenCAPI device with ThymesisFlow could handle a maximum of 4 sections at the time. And once this is done, so once the hot plug is successful, this memory is accessible from any application in the operating system automatically without any further intervention. So essentially what we do is that we extend a bit, the memory model of Linux. So normally you would have sparse mem that sees memory divided in memory sections, and then each section is composed of page frames. And then these page frames would normally be mapped to physical addresses that correspond to where you have your memory mapped, your DIMMs, your memory controller. In this case, instead, the page frames are mapped to that window of addresses that is associated to the OpenCAPI device. So we create then, let's say we divide these page frames in 1 terabyte sections, and each section is linearly mapped to a remote destination, meaning that one section can only be served by a remote machine, but one remote machine could be potentially serving multiple ThymesisFlow memory sections. So the fact that the memory attachment is completely transparent helped us a lot in running evaluation and software, because technically you don't need to not even recompile your software, right? You just run it and you benefit from disaggregated memory. So now I will show you quickly the evaluation, some applications that we have executed on our prototype. And all these results that you see here are going to appear at Micro 2020. So if you want a deeper explanation of it, just join us at Micro in a couple of weeks, in 1 month from now. So we have used the 3 cloud workloads: in-memory database, caching, and Elasticsearch. And also we run stream to see what is the sustained bandwidth, the maximum bandwidth that we can measure. And we compare 2 configurations that are, one is the local versus disaggregated, meaning that an application is running on a node. It either uses a local memory or disaggregated memory, and the scale out versus scale up. So scale out means that I need more memory than what is available in the node, and I get it by running a second instance of the application on another node. Or scale up, which is I still need more memory than what is available to the node, but instead of using the CPU of the other node, I just borrow the memory using ThymesisFlow. This means that scale up uses half of the cost of scale out. So this is to be taken into consideration, into account. Let's start with the experimental setup. As said, we use 2 AC922 servers. Our design is implemented on the Alpha Data 9v3 cards that are OpenCAPI enabled UltraScale Plus FPGAs. And the network that is a circuit network in the initial picture. In this case, is a point-to-point connection between the cards, and we have 100 gigabits per second between the two machines for memory, for disaggregated memory only, right? This is not networking traffic. So stream. Let's first see what is the maximum bandwidth that an application can perceive when using disaggregated memory. And with surprise, we see that we can actually reach the maximum bandwidth for ThymesisFlow, which is 12.5 gigabytes per second, the 100 gigabits per second. And this test was using a stream array big enough for being bigger than any cache that we have in the system. And I also have this dotted line on the top that is just to remember you that the local memory on a P9 has a much higher memory bandwidth. And just to remember that there is at least one order of magnitude difference between disaggregated and local memory. And one other metric that I don't have a chart for it, but I can tell you is that the latency, round trip latency for a memory access is of 900 nanoseconds. So is this performance good enough for running any meaningful workload? This is the question that we asked ourselves, and we have a kind of an answer with a few benchmarks. So first benchmark, VoltDB in-memory database. We run VoltDB. So you see the three configuration: local memory, scale out, and single disaggregated is ThymesisFlow. And I'm showing the throughput of these benchmarks. The clients for VoltDB are those available in the YCSB, the Yahoo Cloud Service benchmark suite. The first thing that we see that we have measured that at most we see a 9% throughput degradation when using disaggregated memory. Even across the other benchmarks that are not shown here, it's maximum 9%. And also another thing that we have noticed is that the scale out has a very similar performance to disaggregated memory, but it is using twice of the cores. So this means that when you are in scale out, there is some remote coordination for queries to happen, right? If you have a join across partitions of a database, this remote coordination will add an overhead that is comparable to what you would get with remote memory, and therefore this means that with ThymesisFlow you can get the similar performance by just using half of the cores. And consider this is a prototype system, right? This is not even close to what you will get with memory inception on P10. The second benchmark we have is Memcached. So here you see the CDF of the get transactions latency. And again, 90% of the transactions only have 7% delay. And even more interesting is that scale out is actually slower than the disaggregated case. And this is because when you use Memcached in let's say replicated deployment, you need to have a proxy in front of all the replicas, because the proxy then will decide which server is serving the specific request. While with the memory disaggregation, we actually can expand in memory, so we can have a bigger key value store, so much more data that we can host, but we don't need to have a proxy in between. So we don't need the delay of a proxy. So far, so good. But it's not good for every application, right? So we have seen, for instance, that for Elasticsearch, is not as good, mostly because of the way how Elasticsearch works, which is a NoSQL kind of, let's call it database. It's not database, where let's say when you do a query, you often go through most of the data rather than doing complex joins between distributed partitions. This means that if you have more cores available, you have more horsepower for going through the records, right? And in fact, it's visible that the scale out is always performing better than the disaggregated case, at least of 45% we have measured. And the other interesting thing is that for some cases, the scale out is even faster than the local memory case, because for instance, in the RTQ challenge, as they are called, they search all the answers in Stack Overflow that feature a random generated tag. So this means that you are likely going through most of the answers in the database. So the more calls you have, the more data you can check in parallel. So for Elasticsearch, we have seen that memory disaggregation is not really offering this is not as appealing as in the other cases, but for some use cases it might still be let's say appealing, in the sense that depends on what kind of trade-off you are looking for, right? You might be looking for cheaper deployment, and you can live with a lower performance. So now I'll just go to a quick demo to show you this is actually working. So we have built an orchestration framework which is a web interface through which we can let's say model the network, the disaggregation fabric between machines that participate to this disaggregated system. In this case, you see 4 machines. Each machine has 2 ports because each FPGA has 2 ports. You see 4 machines, but for the time being, only 2 of these machines, Portaria and Campobasso, are connected to each other. The others are not connected at the moment. We're doing some other experiments. This orchestrator, essentially what you can do is that you can select a node, and you see what is available on the node. Via this orchestrator, you can attach 100 gigabit more to this machine. The orchestrator will find the perfect buddy machine that can borrow you that can lend you this memory. For at the moment, as I said, it can only be this machine, Campobasso. Now, if we make it a bit more nerdy, I can show you. So these are the two machines. Campobasso is going to be the memory donor. So as you see, the machine has 573 gigabytes of RAM available, and almost none is used. And this one on the left is instead the compute node that has the same situation, 500 gigs of memory. So now, I was talking about NUMA before, and if you see, this machine has 2 NUMA nodes with memory, that is NUMA node 0 and NUMA node 8, but there is this NUMA node 16 here that has no CPU, but also no memory. This is where we are going to attach the disaggregated memory. So we go back on the orchestrator, and we just ask the orchestrator, attach 100 gigabytes of memory to this machine. So the orchestrator quickly found who is the buddy. So while the line is orange, what is happening is that the orchestrator is contacting the ThymesisFlow agent on the memory donor, asking for allocating the memory, getting the effective address, and then going to the compute node, configuring the hardware, and hot plugging the memory. So once the link is green, this means that the memory was allocated, and you see here immediately that the node now has 600 gigabytes of memory, and the memory went up. But if you don't believe me, I'll show you here that if you now see the memory available at the compute node side, it magically went up to 600 gigabytes. And the interesting thing is that if you see the memory donor, it's not that the memory available went down, right? Because we're not actually removing the memory physically from the machine. We're just reserving it with the user space process. So the memory was allocated by process and made available. Now, if I go here and I run stream, so this is stream running on the NUMA node 0, you see that the performance is something around 140 gigabytes per second. But by just changing the NUMA binding of this application, now I'm running stream on disaggregated memory. So you see the bandwidth is roughly 12 point something, close to the 100 gigabit per second that you could expect from this design. So as you see, I didn't change the application, I didn't do anything. I just said use this NUMA node for memory allocation. And then if you want, you can even detach. So you just go to this interface and detach the disaggregated memory, and the operation is inverse. So the memory is hot unplugged and freed on the other machine. So I'll just conclude that I have shown you ThymesisFlow, that is the first of its kind open framework for peripherals disaggregation. And the software stack enables completely transparent software-controlled memory attachment. And from this evaluation, it looks like it can be an appealing technology for some applications. So this concludes my talk. If you have any questions, I'm happy to take them. There is actually a question from Paul. So yes, if we used two memory links, we would get the bandwidth would go up. We have done this. It's just still experimental. It's called bonding, but it doesn't go at 200 gigabits per second. We have seen a 30% improvement. This was because at the memory side, we don't use the 256 bytes OpenCAPI transaction, so we are not capable of let's say using the full bandwidth that OpenCAPI gives us, because our design uses the 128 bytes transaction, because since the OpenCAPI transactions are generated as a result of a cache miss, essentially, right? The L3 cache miss, the transaction will always be as big as the cache line. Then there is another question from Paul. So how do we map the OpenCAPI transactions to the Ethernet frames? We do not map OpenCAPI transactions to the Ethernet frames. If I show you, if you see the first slide here, what happens is that the OpenCAPI transaction flows through inside our design, and what we do is that the ThymesisFlow logic is just patching the address and the opcode, but then the network, there is no transport here, right? There is no Ethernet. We just use the physical line for transmitting OpenCAPI transactions to the other side. So what is flowing here? We have a completely custom LLC where we provide a reliable channel, and we also have credits to avoid overflowing of the other side. But it is, let's say, it's all happening at the data link layer. There is no protocol. The memory, yes. So another question from Paul. Yes, the memory is cacheable from the compute side, indeed. Yes, because for the system is just some memory, so it goes through the cache. Yes. So this open, let's say, many discussions, right? At some points, if you have multiple nodes accessing the same remote memory, then you might need to flash your caches before the other node accesses to make sure that the data is in there. But yes, it's cacheable. So I don't see any other question here, and no, I don't see any other questions or hands that are raised. So if anyone has any other question, just ask, or otherwise I will be. So yeah, another question from Paul: how could more than one be connected? Yes, so we have. It's something that I haven't discussed here. We have, besides the patching the address, we have a network identifier that we use for selecting which circuit should the transactions belonging to this section be forwarded to. This means that if you put the circuit switch in between the FPGAs, this switch could be used for creating circuits between multiple machines. But definitely, for instance, right now, even if you had a switch, one node with one FPGA could be connected only to two other remote machines, simply because the FPGAs only have two QSFP cages, so two links, two circuits. We were also considering working with the packet network, but we haven't yet done that work. But this is something definitely interesting. because this would help us in definitely connected to much more machines, right? To have a much more complex fabric topology. Oh, probably. Oh, sorry. There were more questions. Yeah. So one thing is, routing switching is done at the ThymesisFlow logic. So the ThymesisFlow logic is using the network identifier that I have mentioned, is doing the actual routing. The switching, at the time there is no switching. If you put a switch in between, there would be some switching, but only the routing is done by our logic. Potentially, yes, something like Gen Z, for instance, could be used as a transport for going outside of the node, right? It is a possibility. You could use you could use the OpenCAPI between the FPGA, now the FPGA and the CPU, and then have something like Gen Z as a transport for going between the nodes. The session is ending now in 2 minutes, so we have to wrap up. But I will be in the Slack channel if there are more questions, or also there is my email. So if anybody wants to keep the discussion going, I will be more than happy in doing that. So thanks very much everybody for attending this session.